Hi, welcome to Module 8 in Lecture 8. This is the last module in Lecture 8, and it covers a special case of what we talked about in the previous module, which was expectations. In this module, we're going to discuss expected utility. Now, if you remember, we dealt with the general expectation of a function in the previous module that looked like this, assuming there's only one variable x. And this was equal to sum on I, f of xi, times the probability that the random variable x equals xi. Expected utility is the exact same thing, putting a u in for f. So if I stick in a u over here, u of x, and a u of xi over here, you get expected utility. Now it's so commonly used that we actually don't write it as e bracket u of x often, we write it as eu of x, because it comes up everywhere, not only in game theory, but more generally in rational choice theory or expected utility theory. It even comes up in bounded irrational theories or behavioral game theory. Pretty much everywhere you want to assign some personal benefit to some action, you use expected utility if there's uncertainty involved. So that has the same form as before. Again, you just plug the u in there, and you get this. Okay, there's the expected utility. I think I went off the page. There you go. So definition-wise, that's all it is. How do you use it? Well, we've already seen some way you use it. For instance, if you're perfectly risk neutral, which we'll discuss later, then you might have utility just equal to x. In that case, this thing down here becomes sum on xi, which is just the expected value of the distribution. So if you're perfectly risk neutral and have nothing attached to utility but x, this gives you the expected value is the same as the expected utility. But in general, you may have different values. If, for instance, utility is equal to the square root of x, then you would have this to deal with, and so on. Now, I've already done some of these examples before. Right, so for instance, we did the lottery example when you had a 0, you won 0 with 0.99 and you won 10 with 0.01. And the expected value of that lottery was 0.1. Well, if your utility is equal to x, then your expected value is your expected utility. In that case, all you're doing is calculating your expected value to figure out how much you value this particular lottery. And then oftentimes you use that in game theory by comparing it to the cost of playing the lottery. And if the expected value of this lottery, often called P, is greater than the cost, or equal to usually, you're willing to play the lottery. And if it's not, you're not. So that's an example of how to use expected utility right now. There's lots more examples you can think of. Let's do a more complicated example. This example involves an election game, which we have two parties, party A and party B, who are contesting some fair election. In the background of this election is a policy space running between 0 and 1. 0 are the most left-wing policies available, the most liberal policies, and 1 are the most right-wing and conservative policies available. The party's task is to locate simultaneously on this line, and that point which they locate becomes their platform for the election, for the campaign. We're going to assume for this game that platforms are important, that is not just talk, that whatever platform they actually specify during the campaign gets enacted with certainty during the time they're in office should they win. So the winning platform is the one that gets enacted in office. They can't go back on their words. This is obviously not completely true in real life, or maybe mostly true, but it's an approximation for the purposes of this game to make a point. This game, by the way, is a variant of a game produced by Calvert in the '85 paper. Anyway, so they have to locate simultaneously on this thing. What do they want? Well, utility of party A, given some policy that gets enacted, is equal to negative x minus 0 squared. These are quadratic loss functions representing policy preferences. 0 is player A's ideal point, is a left-wing party. This is just negative x squared. And party B wants to get as close as 1 as possible. So this is, again, the same thing as here. It doesn't get simpler at all. It does not get simpler at all. Okay. If you don't remember where these come from, they're a way of representing policies that are utilities that are highest at an ideal point and drop off around the ideal point. In this case, the highest utility for each of these parties is 0, and it gets lower as you go away from the ideal points. Party A gets its highest payoff at point 0, party B at point 1. Okay. So how does this game work? Well, we haven't specified how they win the election yet. To do that, we need to specify who the voters are. In this case, the voters are going to be distributed in some fashion across the line, across this line segment. The median voter, the voter in the middle, we're going to call M, and call the median voter's ideal point M. Now, we can specify the median voter's utility, but really what's important here is whoever gets closest to the median voter wins. Why is that? Well, it relates to the well-known theory in American politics / social choice theory / game theory of Black's median voter theorem. The median voter in general is the voter in the middle, which means there are equal numbers of voters to left or right of the median voter, assuming an odd number of voters. What that means is if you locate on the median voter, then you get the median voter and all the voters to the left, and you win. If you locate on the median voter, you'll say to the right of that, you get the median voter and all the ones to the right, and you win. Point is, you get all those voters. So in a game in which you don't care about policy and you have certainty about where the median voter is, both parties end up locating on the median voter because that guarantees them a tie. Right? Say that again really quickly. Let's see if a line like this, the median voter's over here, you know that with certainty. Well, where should you locate? Well, if I locate over here and you locate over here, then I'm closer to the median voter, so party A wins. Party B will move a little closer to try to win, and party A move closer until they both end up on the median, and then they both tie. Moving away from the median doesn't help them because you move away and then lose the certainty. So this is a very, very, very quick way of going through this particular candidate location game. In certainty. The reason I'm bringing it up now, though, is because under uncertainty it gets really interesting. Now let's say instead of the median voter being known, the median voter is not known, and it's distributed in some fashion according to uniform distribution on this line segment. We'll talk about uniform distributions in the next lecture, but simply put, it means there's an equal chance of finding the median voter anywhere on this line segment. It's the continuous version of, say, rolling a die and having equal chance of getting a 1 through 6. So that's the setup. Now, why is it interesting? Well, we saw very quickly that if there's a median voter with a known position, then there's no reason to locate away from the median voter, no matter where that median voter is. Sure, you can move closer to your ideal point, but then you lose, and you don't get what you wanted. Right? So you can't actually get a better outcome in the election, because if you care about policy, you can't get a better policy outcome by moving closer to your ideal point, because then you don't win, and you don't get to enact your policy. However, if the median is uncertain, there's a trade-off involved. Now, if I move away from sort of the middle of the distribution, then I have less of a chance of winning than before, but I still might win because the median might turn out to be left of the middle because it's random, stochastic. So I might be able to move to the left, and should I win, I get a better policy for me. So there's a trade-off between getting a better policy for me, but winning less often, because the more I move away, the less I win. You can see that by looking at this picture up here. Let's say party A is over here, and let's say party B is over here. Well, the median might end up anywhere, right? If the median ends up in the midpoint this way, party A wins. If the median ends up from the midpoint to the right, party B wins. If party A moves to the left, the midpoint moves to the left too. So party A wins less often because the red area over here gets smaller. So the chance that party A wins decreases. But should party A win, party A is now closer. Party A is now closer to 0, and it makes Party A happier. So there's a trade-off between what you get if you win and your chance of winning. The secret of game theory is trying to understand how to make that choice optimally. We're not going to solve this game here. If you want to solve this game, go to take a game theory class. But the important point in terms of this course, this module, is that there's going to be a trade-off between the chance of winning and where you locate, and that trade-off can be optimized by writing out an expected utility. The expected utility here is going to equal just what we did before, right? It's the sum of the utility at each point that could happen times the probability that that point happens, summed over all points that can happen. Right? That was the definition. Well, what can happen to Party A? Now let's say Party B is located at some xb, and Party A is located at some xa. What's Party A's expected utility? Well, there are two things that can happen. Party A can win, or Party B can win. Let's ignore ties for the moment, because it doesn't really matter that much, but those are two things that can happen. Well, what do you get for that? If you win, then Party A gets the utility for winning, which is the utility you get from locating at xa, giving you a deal point of 0, times the chance of winning, and I'm just going to write probability win here for the moment, and then minus utility for losing times p lose. Now p lose is 1 minus p win because you either win or lose. So it makes it a little simpler. We still need to know p win. Well, first of all, we've written an expected utility out, so that's good. Second of all, we need to know p win, and that's going to relate to the probability stuff we've dealt with before. What's the chance of winning? Is the chance that the voter, the median voter, is between 0, assuming you locate to the left of B, and the midpoint between A and B. The midpoint is this. To derive this, we'll be able to do this in the next lecture where we have to integrate a uniform distribution. But this ends up being the chance that the median is to the left of the midpoint. So this equals a chance that P wins. Then 1 minus this is a chance that that A loses, and then you can go through and maximize accordingly. You do maximize both people's utilities. You do the same thing for Party B with 1s in here and so on, and you can solve this thing out. So two major points that I wanted to sort of express by going through this. The first point is that you can write out the expected utility of more complicated scenarios than a simple lottery just by using the exact same formula, inserting whatever utility you have, whatever utility function you have at a given point that could happen for every point that could happen, and each one of those utilities is multiplied by the chance of that particular thing is happening. That's it. That's how utility works. Now, second thing is that this is actually formed from a CDF. A lot of times we're interested in knowing what the chances are, in game theory, what the chance is that utility, for instance, might be less than or equal to some cutoff. Well, the cutoff might be, say, the cost of the action. If the utility is between, say, some number and the cutoff, you might do the action. If the utility is less than the cutoff, you might not do the action. Well, the chance of being less than a cutoff is a chance of the value turning up less than or equal to some number, which was a CDF. So the CDF also comes up a bunch in game theory, not just in stats. It comes up a bunch in game theory in these kind of contexts when you're trying to understand what you would do given uncertainty. Such that, the last thing I want to mention is the relationship of risk to utility, to expected utility. We discussed this a little bit before when we talked about concave and convex functions in calculus. Here, the stuff we talked about before still holds. So if you have a function like this, then you have what's known as a risk-neutral utility function. So this is risk-neutral. We call this like this, and this is neither concave nor convex. if you have this function, this is a concave function because a line connecting 2 points is below the curve. This is risk averse. And if you have a function like this is a convex function because the line drawing 2 points is above the curve. And this is risk seeking. Now, how can we see these things? We talked a little bit back when we talked about concave and convex and why this was the case. Let's look at it in terms of expected utility now. Well, let's play a lottery in which you have a half chance of getting 2 plus a half chance of getting 0. The expected value of this lottery is 1 using the expected value function formula, which says that it's a chance of getting the first outcome times the first outcome plus the chance of getting the second outcome times the second outcome. That together equals equal to 1. So that's the expected value of the lottery. Because the risk neutral function up here is the same as the expected value formula, right? So plugging u of x equal to x gives you back in the exact same expected value formula of this. Right? Well, then for the risk neutral person in this case, the expected value is exactly the same as the expected utility, and therefore this person does not care, is indifferent between playing a lottery and having expected utility of 1/2, and having someone say, look, forget the lottery, I'll give you, expected utility of 1, and someone saying, forget the lottery, I'll give you 1 right now. This person has an expected utility of 1 for the lottery, and therefore doesn't care where they get the expected utility of 1 from, be it a lottery or a sure thing. They're risk neutral. They don't care about risk. Now, what about risk averse? Now, the expected value is still 1. But what's the expected utility? Well, it's 1/2, but it's not 2 anymore. It's the square root of 2 because utility is the square root of x. This is still the square root of 0, which is still 0. So now you have here the square root of 2 over 2, which is about 0.7 or so. That's less than 1. So this person actually gets less utility for the lottery than they get for taking 1, because utility for 1, right, is just going to be u of 1 equals the square root of 1 equals 1. So if this person gets a sure thing of 1, they say, great, I get 1. The lottery only gets them 0.7. So they would always take the sure thing over the lottery when the sure thing represents the expected value of the lottery. That's part of how you define a risk-averse person. They don't like risk. They prefer the sure thing to a lottery, even when the lottery, when the sure thing is the expected value of the lottery. Right? Finally, you have a risk-seeking. Well, risk-seeking people get 2 squared plus, again, 0 squared. That's going to equal 1/2 times 4, or 2. 2 is greater than 1. Utility for 1 for them is 1 squared equals 1. So they get a utility of 2 for playing a lottery, and a utility of 1 for saying, forget the lottery, I'll just take a sure thing that's equal to the expected value of the lottery. They would prefer the lottery all else equal. They like the gamble. It makes them happy to play the gamble. So a risk-seeking person is someone who would choose the lottery over getting, for sure, the expected value of the lottery. And that's where this risk-seeking part comes from. Right? And again, you can go back to what we talked about for concave and convex functions to note that the risk-averse person finds gains less interesting than losses, whereas the risk-seeking person finds gains more interesting than losses, and these drive behavior. These kind of arguments also pop up in doing prospect theory, which deals with different responses to gains and losses in behavior. It's a deviation from the standard rational choice approach, in that it looks at differences in gains from losses and gains, which requires you to have some kind of reference point that defines losses and gains and all that. That's stuff you might see if you go on in organizational theory, or if you go on looking at boundedly rational models of behavior. But anyway, this is the important point. The expected utility function lets you compute the value to people of games in conditions of uncertainty, and also lets you codify ideas of risk in utilities, which can be really helpful because even though most models tend to assume risk neutrality because it's easier to deal with, because the derivative of x is 1, so maximization is easier. Most people, for most things, tend to be risk averse in a lot of substantive cases, so it's a more reasonable assumption in a bunch of cases, and it helps be able to know how to deal with that fact. Right. That's it. That's it for this module and this lecture as well. In the next lecture, we're going to do a lot of this stuff over again, but now talking about continuous distribution functions and continuous distributions. Thank you very much.